In today's lesson, we're going to be talking about maximum and minimum values of a function. Now, given any function here, that function takes on various maximum and minimum values, and we want to be able to use our calculus and use our derivatives to identify where these max and min points exist. To find these max and min points, recall our last lesson we discovered that if your first derivative was greater than 0, then we discovered the function was increasing on that interval. And likewise, we discovered that if your first derivative was less than 0, then your function was decreasing on that interval. Therefore, we can use our first derivative to identify where a function is increasing and where a function is decreasing. Between those values, which would be here, this point, and this point, the function is experiencing a change in motion. This change in motion causes the first derivative to be 0. These points where your first derivative is 0 are known as your critical numbers. And notice it allows us to find change in motion. And at that change in motion, your function could hit a maximum or a minimum point. Likewise, if our goal is to identify maximum and minimum points, notice our first derivative would be undefined here. But this function hits a minimum at this value. So therefore, we also want to identify points where your derivative is undefined. We define the critical numbers as being all the points where your first derivative is 0 or your first derivative does not exist. So now that we have our critical numbers, we will be able to identify all of these points here and this point here. We need to get a better definition of what it means to be a maximum and minimum value. All right, so we want to be able to identify maximum and minimum points that a particular function takes on. Well, the question becomes is what is a maximum and what is a minimum? In this example here, notice if we are given this function and I went ahead and took my derivative and I found my critical points. My critical points here would be this value here, this one here, and this one here. There are no points on this function where the derivative is undefined, so our critical values would just be these three that we would find. These 3 points experience a change in motion, going from increasing to decreasing or decreasing to increasing, and these points would be known as your local maximum or minimum values. This point right here, locally, within this area, is the largest, so it would be determined as a local maximum. Likewise, this point, within its local region of this interval, a subset of the domain of the function, is locally a maximum. So we can label that as a local maximum. Likewise, this point here, locally is a minimum. Now we have terminology to represent local maximums and local minimum values that a particular function takes on. But what we're interested in finding as well is the absolute maximum and absolute minimum that a function takes on. Well, to examine that, you not only have to examine points where your derivative is 0, you also have to identify the endpoints of your function. In this case here, this point and this point. Notice here, of all of these 5 points, this point here is my smallest. Therefore, this endpoint would be known as an absolute minimum. Also notice here, the largest point that exists in this function is actually this one here. Because of that, we will relabel this as an absolute maximum. So therefore, our function here has an absolute maximum right here and an absolute minimum down here. And the function hits a local max and a local min at these 2 values. So therefore, you can see the importance of not only examining your critical values, but also your endpoints when you're trying to find absolute maximum and minimum values. So in summary, to identify the absolute maximum and minimum values of a function, you must examine all the points where the derivative is 0 or undefined in addition to your endpoints of your function. Let's take a look at some examples. So for the first example here, notice we're going to be focusing our attention on the idea of absolute maximum and absolute minimum first. So for this function here, if you take a look here, they give us a function f at x. It's going to look like this here, and it's on this interval. Okay, so if I want to find the absolute maximum and minimum, what we have to find is all the critical values. So I'm going to go ahead and take my first derivative, in which case we get 3x squared plus 12x plus 9. Setting this equal to 0 and factoring out a 3 and doing a simple factoring on the inside, we end up finding here that x equals -1 and -3 on my 2 x coordinates where my f prime is 0. So now that we have the x coordinates of the critical points, we also have to examine the endpoints. So therefore I'm going to examine f at -1 f at negative 3, f at negative 3.5, and f at 1. So you'll notice here I'm taking the endpoint here, f at minus 3.5, and I want to see whether that is an absolute max or min. Likewise, I'm taking f at 1, and I'm going to see whether that is an absolute max or min. And then I'm also taking my two critical points here, because these are the points where your first derivative is 0. And because of that, that is a change in motion, and that means it either goes from increasing to decreasing or decreasing to increasing. So we want to examine these values and see. So evaluating my function at its critical values and its endpoints, we're finding here the following values. F at negative 1 is negative 2, f at negative 3 is 2, f at negative 3.5, so the one endpoint here is 1.125, and lastly f at 1 is 18. So if we're going to go ahead and grab our maximum value, that's going to be 18, and the minimum value is negative 2. Therefore, for this graph here, the absolute maximum occurs when x is equal to 1, and the absolute minimum occurs when x is equal to negative 1. As a point, that point would be 118, and the absolute minimum, or expressed as a point, will be negative 1, negative 2. So the following function here has an absolute maximum at 118 and an absolute minimum at negative 1, negative 2. Let's take a look at the graph of this function. So here's a graph of the function above that we had just found the absolute maximum and absolute minimum values of. Notice right here, we have our first critical value we had found. This is f prime at negative 3. And in this case here, you know that tangent equation was 0. That was one of our critical values. Another critical value we found was f prime at negative 1. We found that was also 0. And we grab this critical value here. And then lastly, these were our endpoints, 118, and then negative 3.5, and 1.125. So notice the importance of checking your endpoints. In this situation here, had we just considered the critical values of our function, we would have thought this would have been the absolute maximum, and this would have been the absolute minimum. But that was not the case. Obviously, we have an absolute maximum here at our endpoint. Likewise, had we only considered the endpoints and not our critical values, we would have missed a absolute minimum at negative 1 and negative 2. Let's look at another example. So for this question here, we want to find our absolute maximum and minimum. So in this situation here, I'm going to go ahead and take our first derivative and find our critical numbers. So using the product rule, we have the first times the derivative of the second plus the second times taking the derivative of the first, you get 2/3 x to the minus 1/3. Setting this equal to 0, we have x to the 2/3 plus 2/3 times 5 plus x times x to the minus 1/3. Cleaning this up, we get x to the 2/3 plus 2 times 5 plus x over 3x to the 1/3. Getting a common denominator, multiply top and bottom by 3x to the third, and in which case here we get 0 equals 3x plus 2 times 5 plus x over 3x to the third. This becomes 3x plus 10 plus 2x over 3x the third, which is 5x plus 10 over 3x to the third. Setting this equal to 0 and factoring out a 5 out of the numerator, we find that the one value where your first derivative is 0 is going to be x equals negative 2. In addition, we want to make note of points where the derivative is undefined. So we're also going to identify x equals 0. So we have our two critical numbers here. In addition, we want to examine our endpoints, and the endpoints of this function were negative 5 is less than x is less than 1. So we also have to examine x equals 1 and x equals negative 5. Of these four values, we will be able to identify the absolute maximum and or absolute minimum. Evaluating this function at the critical numbers and endpoints, we get 4.8, 0, 6, and 0. So we can see here that the function hits an absolute maximum at the point 1 and 6. Absolute minimum values occur at two different locations. The first is at the point 0, 0, and the second is at the point negative 5 and 0. Let's go ahead and look at the graph of this. So here's a graph of our function g at x. Notice that this value here, f prime at negative 2 was 0, and that was one of our critical points, i.e. the derivative at that value was 0. Also, don't forget we grabbed this point here. And this point here, as you can see from the graph, meets at a peak. And because of that, we have a point of non-differentiability. So we had grabbed this point because the derivative did not exist at 0, but it turned out that this was one of our absolute minimum points. And likewise, these were our endpoints here, negative 5, 0, and 1, 6. So going ahead and graphing this here, we noticed that we ended up getting a absolute maximum at one of the endpoints, and we actually achieved 2 absolute minimums, one at the other endpoint, and the other absolute minimum was found when we were identifying our critical values where that first derivative was undefined. All right, that concludes today's lesson. And remember, when you're looking to find the absolute maximum and absolute minimum value of a function, examine the critical values in addition to the endpoints. Thank you.